Hi boys and girls, this is lecture 8.2. Our review topic today, volume of a solid. Let's start with a solid of revolution. What is it? It's a solid figure obtained by rotating a plane curve around a straight line known as the axis of rotation. Here is the curve and here is the axis of rotation. Notice the area that is formed between that curve and the axis of rotation. Rotating it around the x-axis generates this solid of revolution. How can we find the volume of a solid of revolution? Integrals are used to calculate the volume of a solid of revolution. Notice I have here the curve y equals the square root of x. The axis of rotation is the x-axis. If I rotate this curve around the x-axis, this solid of revolution is generated. The cross-sections perpendicular to the x-axis are circles. I have a few representative circles drawn here, but there would be an infinite number of circles from A to B on this interval. Every function value on the curve would represent a radius of one of those circles. Let's look at this circle more closely. Notice the radius is the function value at a specific x on the interval. So we need to add up the areas of an infinite number of circles, and that will give us the volume of this solid. Well, the only thing that can add up an infinite number of areas of circles is the integral. So we're going to set up an integral from A to B and add up an infinite number of areas of circles. In this case, the radius is the function curve. We put pi on the outside because it's a constant, and this is the generic setup of an integral used to calculate the volume of a solid of revolution. So in our circle, if the area is pi r squared, and our function curve in this case is the square root of x, and that's the radius, then the area of this circle is pi square root of x squared. So let's set up an integral and find the volume of this solid. Here is the setup for this integral. Pi on the outside from A to B, the function curve, the radius squared dx. So we'll have on the outside pi. Our interval here is from 0 to 4. Our function curve, square root of x, that's squared because the radius is squared when you're finding the area of a circle. And of course, we're integrating with respect to x. Let's simplify this integrand. 0 to 4, this just becomes x dx. Now we integrate pi 1/2 x squared, evaluated from 0 to 4. This gives me pi times 1/2 times 16. Putting in the lower endpoint of integration does not generate another value, so this becomes 8 pi cubic units. The volume of this solid of revolution, 8 pi cubic units. What if we change the axis of rotation? In this case, let's change it to the y-axis. If we're going to evaluate an integral with respect to the y-axis, the function needs to be in terms of y. Therefore, y equals the square root of x becomes x equals y squared. And revolving this function curve around the y-axis generates this solid of revolution. The cross sections are still circles, but they are now perpendicular to the y-axis. And the radius of each circle is the distance from the y-axis to the function curve y squared. Here is that representative circle. The radius is y squared. Since the area of a circle is pi r squared, the area of these circles will be pi y squared squared, or pi y to the 4th. So here's how we'll set up our integral. From C to D, and that will be endpoints of integration on the y-axis, pi r squared dr. But since the radius is the function curve f of y, that will be from C to D pi f of y squared dy. We put pi on the outside of the integral since it's a constant, and then from C to D f of y squared dy. This integral will give the volume of the solid rotated around the y-axis. Let's set up our integral and calculate the volume of this solid. Pi on the outside. In this case, we'll be integrating from 0 to 2 on the y-axis, So those will be our endpoints of integration. The radius of the circle is the distance from the y-axis to the function curve y squared, and this is radius squared, so y squared squared dy. Let's simplify this integrand. Pi from 0 to 2, y to the 4th dy. And now we integrate. Pi 1/5 y to the 5th, evaluated from 0 to 2. Pi 1/5 times 32. And once again, inserting the lower endpoint of integration will not change this answer. So this becomes 32 over 5 pi cubic units. The volume of this solid of revolution, 32 over 5 pi cubic units. What if there's a hole in the middle of the solid we're generating? Here we have the function curve cubed root of x and the line 1/4 x. If we take the region enclosed by these two function curves and revolve it around the x-axis, the solid that is generated will have this opening in the middle. The way we would calculate this volume is first to calculate the volume using the outer curve, as if there were no hole in the middle. Then we will calculate the volume using the inner curve. Once we have that volume, we would subtract it from the volume we calculated earlier. The result would be the volume of the solid with the opening in the middle. Therefore, we're going to need two circular cross-sections, one with the radius using the outer function curve and one with the radius using the inner function curve. Here is that representative cross-section. The blue circle represents a cross-section of the volume of the solid using the outer radius. The white circle represents a cross-section of the volume of the solid using the inner radius. If we punched out this white circle, the result would be a cross-section for the region we're trying to find the volume of. Notice that the outer radius is the distance from the x-axis to the outer function curve, and the inner radius is the distance from the x-axis to the inner function curve. Therefore, the area of this blue region will be the area pi r squared outer radius minus pi r squared inner radius, where the outer radius is f of x, the distance from the x-axis to the outer function curve, and the inner radius is g of x, the distance from the x-axis to the inner function curve. Therefore, we'll be calculating the area of a circle using the outer radius and subtracting the area of the circle using the inner radius. Let's start with two integrals, one that calculates the volume of the solid using the outer radius, and then another calculating the volume of the solid using the inner radius. Subtracting this volume from this volume will give the volume of the solid we're generating, the one that has the opening in the middle. We'll consolidate these integrals into one. Pi on the outside, from a to b, the interval on the x-axis, outer radius squared minus inner radius squared, where the outer radius will be the function curve f of x, and the inner radius will be the function curve g of x. Let's set up this integral. We'll have pi on the outside, and we'll be integrating from 0 to 8 on the x-axis, the outer curve, cubed root of x, quantity squared, minus the inner curve, 1/4 x, quantity squared, and of course we'll be integrating with respect to x. Let's simplify the integrand. We'll have pi on the outside. From 0 to 8, this becomes x to the 2/3 minus 1/16 x squared dx. And when we integrate, we'll have pi times 3/5 x to the 5/3 minus 1 over 48 x cubed evaluated from 0 to 8. This becomes 128 over 15 pi cubic units. Here are a couple of formulas to keep in mind when you're calculating the volume of a solid of revolution. If your solid has no hole in the middle and the axis of rotation is the x-axis, here is your integral setup. Pi on the outside, endpoints of integration a to b, an interval on the x-axis, the function curve f of x squared dx. If the axis of rotation is the y-axis, pi on the outside, c to d, an interval on the y-axis, the function curve f of y squared dy. If your solid does have a hole in the middle, and the outer radius is f of x or f of y, the inner radius is g of x or g of y, and the axis of rotation is the x-axis, here is your integral setup. Pi on the outside, the endpoints of integration, the interval on the x-axis, a to b, the outer function curve, f of x squared, minus the inner function curve, g of x squared, dx. If your axis of rotation is the y-axis, pi on the outside, c to d, the endpoints of integration, an interval on the y-axis, the outer function curve, f of y squared, minus the inner function curve, g of y squared, dy. What if the axis of rotation isn't the x-axis or the y-axis? In this example, we're going to determine the volume of the solid obtained by rotating the region bounded by y equals x squared minus 2x plus 2 and y equals x plus 2 about the line y equals 6. The resulting solid will have a hole in the middle, so we'll need an outer radius and an inner radius. This is a representative circular cross-section of the region. To determine the outer radius, we'll need to know the distance from the axis of rotation to the outer curve, but everything is measured from the x-axis. So in order to quantify this distance, we'll have to say 6 minus the distance to the curve. 6 minus this distance will be the radius we're looking for. In order to quantify the inner radius, we'll need to find the distance from the axis of rotation to the inner curve. Again, since everything is measured from the x-axis, we'll find that distance by saying 6 minus the distance to the function curve, x plus 2. That resulting distance will be the inner radius. So the outer radius can be written this way. 6 minus the quadratic, x squared minus 2x plus 2. Let's simplify this expression. 6 minus x squared plus 2x minus 2 gives us negative x squared plus 2x plus 4. That's the outer radius. The inner radius can be written this way. R equals 6 minus the line, x plus 2. Let's simplify this expression. 6 minus x minus 2 gives us negative x plus 4, the inner radius. Now let's set up our integral. We'll need pi on the outside, and we'll be integrating from 0 to 3. The outer radius, negative x squared plus 2x plus 4, quantity squared, minus the inner radius, negative x plus 4, quantity squared, and of course we're integrating with respect to x. We'll need to square this trinomial, square this binomial, combine like terms, integrate, evaluate at the endpoints of integration, and then our volume will be 153 over 5 pi cubic units. We can also use the integral to find volumes of solids with known cross-sections. This won't be a solid of revolution where the cross-section is a circle. Rather, a region on the coordinate plane will form the base of a three-dimensional shape whose cross-section is a known geometric region, such as a square or a rectangle or triangle or perhaps a semicircle. Since the integral will add up an infinite number of areas, we simply need to quantify the area of our cross-section and let the integral add up the infinite number of those areas on our interval. For this problem, we're going to find the volume of the solid whose base is bounded by the x-axis, the line x equals 4, and the function curve y equals the square root of x. The cross-section is a square, perpendicular to the x-axis. This square is a representative cross-section, and you can see that the length of a side is the distance from the x-axis to the function curve square root of x. Since the area of a square is side squared, the area of our squares will be the square root of x quantity squared. Let's set up our integral. Now remember, we don't need pi for this integral because our cross-section is not a circle. The reason we used pi before was because the area of a circle is pi r squared, but the area of a square, side squared. There's no need for pi. We're integrating from 0 to 4, and the length of our side is the square root of x. The distance from the x-axis to the function curve. Side squared means we'll square the square root of x, and then of course we're integrating with respect to x. Let's simplify this integral. 0 to 4, x dx. When we integrate, 1/2 x squared, and we'll evaluate from 0 to 4, which gives us 8 cubic units. And that's the volume of our solid. Here's a three-dimensional representation of the solid. Let's do a couple of free response questions from previous AP exams. This question is from the 2007 AP exam. Let R be the region in the first and second quadrants, bounded above by the graph of 20 over 1 plus x squared, and below by the horizontal line y equals 2. Letter A says find the area of R. So we'll need to take the function curve and subtract the horizontal line y equals 2 to find this area. This is on the calculator allowed section of the exam. So let's find the endpoints of integration by setting these functions equal to each other. 20 over 1 plus x squared is equal to 2 when x is equal to plus or minus 3. Once you have the endpoints of integration, you can set up your integral from -3 to 3 of the function 20 over 1 plus x squared minus 2, and you're integrating, of course, with respect to x. Using the integrate function on your calculator, you find that this area is 37.961. Now let's look at letter B. Find the volume of the solid generated when R is rotated about the x-axis. So this is what we're going to see. Our shape rotated around the x-axis gives us a three-dimensional solid with a hole in the middle. This means we're going to need an outer radius and an inner radius in our integral. The outer radius is the distance from the x-axis to the function curve 20 over 1 plus x squared. The inner radius is the distance from the x-axis to the horizontal line y equals 2. So let's set up this integral. We will need pi since the cross-section is a circle, and we'll be integrating once again from -3 to 3. The outer radius is 20 over 1 plus x squared, quantity squared. The inner radius is 2 squared. And of course, we're integrating with respect to x. Using our calculator, we find that this volume is 1871.190 cubic units. Now let's look at letter C. The region R is the base of a solid. For this solid, the cross-sections perpendicular to the x-axis are semicircles. Find the volume of this solid. So let's look at our original region. Now we're going to have a three-dimensional solid, but not a solid of rotation. Instead, this region will be the base of our solid, and the cross-sections will be semicircles, perpendicular to the x-axis, from -3 to 3. So we have to quantify the area of this semicircle and set up an integral which will add up those areas from -3 to 3. Well, the area of a semicircle is 1/2 pi r squared. So we can set up an integral from -3 to 3 with 1/2 pi on the outside. This is letter C. We just need to quantify what r is. We can see that the diameter of the semicircle is the difference between the function curve and the horizontal line y equals 2. So that's going to be 20 over 1 plus x squared minus 2. If that's the diameter, then half of that is the radius. So the radius squared for this particular integral will be 1/2 20 over 1 plus x squared minus 2 quantity squared dx. Using our calculators, we find that this volume is 174.268 cubic units. Here are the scoring guidelines for that question. Notice that one of the 9 points is for the correct endpoints of integration in the integral in A, B, or C. Then for letter A, 1 point was given for the integrand, 1 point for the correct answer. In letter B, 2 points were given for the integrand, 1 for the correct answer. And in letter C, 2 points for the correct integrand and 1 for the correct answer. For our last example, we'll revisit a free response question we've seen before from the 2009 AP exam. If you recall, in a previous lecture, we found the area of this region R, and that was 4/3. Letter B says the region R is the base of a solid. For this solid, the cross-sections perpendicular to the x-axis are squares. Find the volume of the solid. So our cross-sections will be squares. We need to quantify the area of the square and let the integral add up the infinite number of those areas from 0 to 4. Well, the area of a square is side squared, and the length of the side of our square is the difference between these two function curves. So our side will be the upper curve, the square root of x, which I'll write as x to the 1/2, minus the lower curve, x over 2, which I'll write as 1/2 x. And our integral then will have from 0 to 4, x to the 1/2 minus 1/2 x, quantity squared dx. We'll square that binomial to simplify the integrand. 0 to 4, x minus x to the 3/2 plus 1/4 x squared. And now we'll integrate. Remember, this is on the calculator not allowed section of the exam, so this is all manual integration. We'll have 1/2 x squared minus 2/5 x to the 5/2 plus 1/12 x cubed, evaluated from 0 to 4. And this will give a volume of 8 over 15 cubic units. All right, now for letter C. Write, but do not evaluate, an integral expression for the volume of the solid generated when R is rotated about the horizontal line y = 2. Let's see what this will look like. We have this region now being rotated around the horizontal line y = 2. This will be a solid with an opening. So we'll need an outer radius and an inner radius. Remember, the outer radius is the distance from the axis of rotation to the outer curve, and the inner radius will be the distance from the axis of rotation to the inner curve. The way this will be quantified is from the x-axis. So this distance to the outer radius from the axis of rotation will be 2 minus the function curve x over 2. This inner radius, the distance from the axis of rotation to this function curve, will be 2 minus the distance to that function curve, the square root of x. So let's set up this integral. Since this is a solid of rotation, we will need pi. We're going to be integrating from 0 to 4. Our outer radius will be 2 minus the outer function curve, which is the line, 1/2 x, quantity squared. We'll subtract from that the volume that is formed from the inner radius. That inner radius will be 2 minus the inner function curve, the square root of x. Quantity squared. And of course, this will be integrated with respect to x. For this question, we just need to set up the integral. We don't need to evaluate. And here are the scoring guidelines for this question. For letters B and C, we see that 1 point was given for the correct setup of the integrand, 1 for the antiderivative, and 1 for the correct answer. For letter C, 3 points were given, 1 for the limits and the constant, that's pi, and then 2 for the integrand. Tip number 2 for the AP Calculus AB exam. Do not round partial answers. Avoid rounding your results until the very last step of your process. There is a function in your calculator which will allow you to store the unrounded values so you can use them in further calculations until you get to the final step of your process. Common student error number 2. Many students assume that if the first derivative at a certain x value is 0, then that point is definitely a maximum or a minimum value, but that's not necessarily the case. Remember that you have to show that the first derivative changes sign on either side of that value to verify that it is indeed an extrema. That's it for today's lecture. I may have introduced a domain issue here, but you get the idea. God bless you, boys and girls.